Hi everyone, it's Mrs. Brimlow, and today we're going to talk about substitution with systems of equations and what it looks like when you have your special cases. By special cases, I mean no solution or infinite solutions. So when we worked with graphing, we learned with systems of equations, there are three different types of solutions. One solution where the two functions intersect at one point. We also have no solution when they're parallel lines, they never cross. And three, we have overlapping lines or infinite solution where it's the same function, same equation, usually just written in different ways. So how will that look like algebraically if we had to solve using substitution? Once again, I'm not sure what page this is in your packet since I don't have the packet, but it is linked in Canvas and the page looks like this. Okay. Just like before, I'm going to use one colored highlighter. I have a calculator ready. All materials you should have as well. Okay. So a system of linear equations might have one solution, no solution, or infinitely many solutions. Your friend is solving an equation and her last line of work says 2 equals 2. What does this mean? So I have to ask myself, does 2 equal 2? The answer is yes. 2 is always going to equal 2. So when I solve an equation and get an answer that looks like that, that means that the equation has infinitely many solutions. A lot of people get tripped up like that. It almost seems too simple, like a trick questions, but it's not. Same with the next one. As your friend is solving a different equation and the last line of work says 2 equals 1, what does this mean? 2 is never going to equal 1, ever. So if that's all we're left with, all the variables cancel out, that means there is no solution. So the equation has no solution. Okay. All right, so let's go ahead and use substitution to figure that out. So in substitution, we need one variable solved for itself, and we replace its expression into the next equation. So we're going to replace y in our second equation with x plus 4. Notice that there's a 4 in front of that y, meaning we're going to have to distribute since we have a coefficient. So negative 4x stays the same plus 4. I'm going to open up a set of parentheses to separate my coefficient of 4 that's in front of y with my expression that I have to replace it with. Okay? So we've substituted x plus 4, what the value of y is, according to our first equation, into our second one. So now you can see the only variable we're working with is x. Okay? So now I'm going to follow the steps of solving. So if I am to multiply or distribute that coefficient of 4 into the parentheses, negative 4x at the beginning stays, plus 4x plus 16 equals 3. Okay. Next, I'm going to combine my like terms. So negative 4x and 4x, they are opposites. It's like saying I have $4 and I spend $4. These will zero each other out, leaving me with 16 equals 3. Okay. Is 16 ever going to equal 3? The answer is never. They're never going to be the same. Since our variables canceled each other out, leaving me with just this, that tells me the type of solution I'm going to have, which is no solution. If I was to graph these equations, they would look like parallel lines because they would never cross. Okay. So this is an example of solving a substitution system of equations with substitution and getting a no solution answer. All right, next one. Y equals 3x minus 2. So we're going to replace 3x minus 2 with y in our next equation. Okay. Once again, notice it has the coefficient of 2. Therefore, I need to put parentheses around whatever I get for y. So negative 6x plus 2. I'm going to open those parentheses and I'm going to replace it with 3x minus 2 equals to negative 4. I stop and do a quick check and see that I'm only working with one variable now, x. So following our steps for solving equations, I'm going to distribute the 2. Okay. And now I'm going to combine like terms if possible, which I can, negative 6x and 6x. Those will zero each other out. They are opposites, leaving me with negative 4 equals negative 4. This is a true statement. The first one was not a true statement. That is not balanced. This one is exactly balanced and always will be. So this has infinitely many solutions. Okay. And if I was to graph this, it would be overlapping lines. So it would end up looking like or being the same line. Okay. All right. So you're going to finish these two problems. There is an activity in Canvas or there is a worksheet in the packet that goes along with these notes that you can do for practice. If you have any questions, let me know. And